Okay, welcome to Authors at Google. Thanks everybody for coming. This is the second talk I've arranged, and so I'm really happy to have you all here. For the past 15 years, David Mindell has been combining engineering and historical research to investigate the evolution of humans' relationships to machines. His engineering work has been primarily in the field of deep ocean robotics and archaeology. He's founder and director of MIT's Deepwater Archaeology Research Group, focused on exploring the deepest parts of the world's oceans. As a research engineer at Woods Hole Oceanographic Institute, he developed the control system and pilot interface for the Jason submersible vehicle. His most recent book, which you will find scattered around, Digital Apollo, explores how human pilots and automated systems work together to put a man on the moon. His current research involves the Laboratory for Automation, Robotics, and Society, which examines human-machine relationships in extreme environments, including the deep sea, but also spaceflight, military robotics, aviation, and surgery. Here today to talk about some of his latest work, David Mindell.
Thank you, Owen. Thanks for inviting me. Hello to everyone online. As Owen mentioned, I've been working on robotics in extreme environments for a long time. And the talk I'm going to give today is observations, things we can learn from autonomy and robotics in extreme environments that are helpful to more terrestrial and everyday environments in which, as you all know, autonomy and robotics are coming. Driverless cars, robotic surgery, practically any place where the human relationship to a particular task is changed or troubled by robots. This is a sort of précis of a book I'm working on that'll be out next year called Our Robots Ourselves: How Robots and Autonomy Are Transforming Human Experience, from Viking Penguin. So this is a kind of 20,000 foot or 250,000 mile overview of that book. And I'll start with a headline from the Wall Street Journal Online. This is about April 5th, so just about a month ago. Navy drones with a mind of their own. Newly unveiled technology runs on tablet and enables unmanned aircraft, with a picture of this aircraft called ACUS, which was sponsored by the Navy. And I'll come back to this later on in the talk, but I want to just sort of highlight the headline: Navy drones with a mind of their own. Kind of classic press coverage of autonomous systems, encapsulating in those few words, you know, all of the stereotypes and kind of media imagery around autonomy, which is very broadly held, not just by reporters, but also by the public. Then I'm going to back up a little bit and go back into the undersea realm and start with this family tree of vehicles, which comes out of the Woods Hole Oceanographic Institute and starts down at the bottom with manned submersibles like Alvin, which you may well have heard of. I'll say more about that in a minute. Goes on to the remote vehicles that are tethered and cabled to the ship, like Jason. Owen mentioned I worked on Jason for a while, some of the more advanced versions of that. And then into these autonomous systems, the Remus, Abe, Seabed, Sentry. Actually, Nereus was just lost last week at about 10,000 meters. It imploded. One of the reasons it's good to build autonomous vehicles. The Remus vehicles found the wreckage of the Air France 447. Seabed and Abe and now Sentry are hard at work sort of science vehicles looking at hydrothermal vents. And the implication of this family tree is there's a kind of autonomous technological progress that moves from manned to remote to unmanned or autonomous. And that's, you know, very much represents the point of view that I had and that everyone I worked with had in the 80s when we started building the first remote vehicles. These were going to be the way of the future. Robots were going to supersede human visits to the seafloor. Alvin at that time had been diving since the early 60s. So already in the late 80s it had 25 years of experience and brought and still brings 3 people to the seafloor down to about, these days it's 6,000 meters, and, you know, sort of puts the human eyeballs directly on the seafloor. And so you have that, whoops. I don't want the Baston Marriott, Cambridge, whatever that is. So you have this human vehicle. And the scientist who led Alvin's use as a scientific tool during the late 60s and 70s was this guy, Robert Ballard, who I'm sure you've heard of. And in the early 80s, he actually came to MIT to one of my teachers, Tom Sheridan, although he wasn't nearly my teacher yet, and helped develop this idea of telepresence on the seafloor. No longer do we need to send people. Now we have remote fiber optic cables. There's a sort of garage that maybe has some sonars on it, hangs off the ship, and now you've got a little remote robot floating around down here. And this image is actually published in National Geographic in 1981. Ballard said, manned submersibles are obsolete. Manned submersibles are doomed, actually, is what he said. He was quoted in the Cape Cod Times as saying that, marked a big split from the Alvin group. He went off and started his own lab to pursue this vision. One of the early vehicles from that vision, which is basically just the towed sled part without the robot, was actually the thing in 1985 that discovered the wreck of the Titanic. But most people think Alvin discovered the Titanic. And the reason is because they went back to the Titanic 2 years in 1986. And the configuration was Alvin with this little teeny remote robot, Jason Jr. It was kind of the predecessor to the Jason robot. And Alvin would sit on the deck of the Titanic and dive. Jason Jr. would dive, remotely controlled by a human operator with a little Sony Watchman, if you ever remember what those were, camera, and actually dive down the grand staircase of the Titanic. And I have a chapter in the book describing that expedition because there was literally this tension between the remote robot people and the Alvin people who were worried about being superseded. In fact, the crew of the ship baked a cake with Ballard's quote that said, "Man submersibles are doomed." And before they would let him to dive in Alvin, they made him eat that cake, literally forcing him to eat his words as though he was clawing back to use this, what they found very capable man submersible. And then the remote robot was added to that. And I put these two images up because they're interesting in that the Time magazine image of the dive has only Alvin. It doesn't even show the little robot, Jason Jr. And the National Geographic image, which is illustrating an article that Ballard wrote, has only Jason Jr. and no Alvin. So you can see there's two very different interpretations of that event. And lest you think, I mean, these already brought this event to public prominence, but this scene basically is the opening scene of the second most highest grossing film ever made. Jim Cameron's film of Titanic reenacts in a kind of Hollywood version this scene. So from the kind of late 80s, early 90s, you have this question being raised sort of in the public discourse about what is the value of remote presence versus physical presence on the seafloor. I joined the group just a year or two after that expedition and began working on this vehicle, Jason, which has this light fiber optic cable that brings electric power and sends telemetry and video back up to the surface. And then later in the 90s and much more in the last 10 years, these autonomous vehicles have come online. And what we found through all this was that the advantages of the remote and autonomous vehicles were not usually the things we expected. For example, they weren't cheaper and they weren't safer. But they did radically change the nature of the work. With the remote vehicle, it meant that rather than having 3 people in the sphere of the submersible, one of whom was a pilot, 2 of whom were scientist observers, they would go down in the morning, spend all day on the bottom, come back up, tell everybody in a meeting what they saw. With Jason, you had the entire science party, maybe 40 people, watching on the surface ship in real time. And it was a very different kind of collective scientific experience to do that exploration with really profound implications. And gave you a tremendous sense of presence on the seafloor. Not least of it from all the other people who you're sharing the experience with and different scientists telling you what you were seeing. In the case of shipwrecks, we work with archaeologists. Similarly, the autonomous systems, the original idea was you'd send them out and they'd go do the thing and come back. But parallel with this was the rise of a technology of acoustic modems. And even if you could only get low baud rate text messages, you still always wanted to stay in touch with this thing as much as you can. But that's since developed in a much more sophisticated sense of autonomous vehicles in the ocean have, depending on where they are, because of the nature of the acoustic channels, you have very different levels of bandwidth moment to moment almost. And now Woods Hole is developing optical modems that are almost like street lights. If you picture one of these lights kind of hanging down, and then anytime you're within seeing range of that light, you can get 10 megabits per second of data back and forth, and then you may swim away. And that, so you're really always in this mode of sort of autonomous and sort of remotely controlled. Then you zoom out a little bit, as we had to with these vehicles, and think about what's really going on. You have a ship out there on the ocean, and the vehicle dives maybe for a day and comes back, and then you take off the data and you recharge the batteries and send it back out again. Maybe even have 2 or 3 of those vehicles working. And so what you really have is a collaborative system with a manned vehicle, i.e. a ship, one of the oldest, most traditional manned vehicles we've ever had, and an autonomous vehicle. And what you call autonomy is really fairly well bounded between these episodes of human intervention. So that's one of the early lessons. And this image, which is actually Andy Bowen's image, who was the designer of the Nereus vehicle, which, as I mentioned, was just lost last week, captures some of that kind of fuzzy world where what's human, what's remote, what's autonomous is constantly blurring. And these are not categories that are really all that useful to us anymore. Again, you have the acoustic modem here during a survey, a kind of optical spotlight kind of modem, other kinds of modalities. Maybe there's a buoy and you exchange with light. And there's a whole very rich period right now experimenting with all these different combinations. So lesson number 1 is just that human remote and autonomous systems are evolving together. You don't have this kind of replacement of human systems by autonomous systems. And they all interact and affect each other. For example, there's a new Alvin just came out, just finished its sea trials actually, fully upgraded, has a new pressure sphere. All the electronics and the software in the new Alvin are taken out of the autonomous vehicles, right? So all that software, all the navigation, all the interesting sort of SLAM modeling of the seafloor that gets done, now gets done inside the sphere in Alvin. Changes what it means to be an Alvin, changes what it means to be physically present on the seafloor. But how is Alvin not a autonomous vehicle that you sit inside? Okay, and that's a bigger question for a lot of other arenas. How is a modern jetliner not an autonomous vehicle that you sit inside? And those questions are constantly coming up in the aviation domain as well. So what the book does, it starts with the undersea story, but then goes into 3 other extreme environments, really. One is remote warfare with the Predator and Reaper operators who are doing things very, very similar to what we learned how to do undersea, although the implications are quite different. Then in the aviation domain and what's happening in commercial aviation with different technologies in the cockpits, heads-up displays, particularly synthetic vision displays. How is this changing the roles of what the pilots are doing? How might it change in the future? What are the cautions we've learned, because there have been some really scary accidents around that? And then into the remote spaceflight realm, particularly looking at the Apollo landings, which I'll come to, which I've already written about, and the Mars exploration rovers, where even with a 20-minute time delay and relatively limited data bandwidth, the scientists who work on that stuff still have a tremendous sense of presence in that Martian terrain. So the sense of presence is not exclusively dependent on high-def video and real-time feedback. So the overall goal is to move beyond some what I'm calling these kind of 20th century ideas of present versus not present, manned versus unmanned, human operated versus autonomous, but rather thinking about mixes of all these things, new ways of being present. And the questions I'm interested in asking is, where are the people? What are they doing? When are they doing it? In many cases, what you consider autonomy really has to do with human intention and being uploaded and programmed at an earlier point in time before it's executed, through what bandwidth and what time delays. And then the last one, which is the kicker for a lot of the really passionate stuff, is why does it matter and why should anyone care? It turns out people care a lot. Even if the cognitive experience of warfare operating through a remote vehicle 6,000 miles away is very, very similar to the cognitive experience of operating the same sort of system from an aircraft at 35,000 feet. The physical presence of the body has a huge cultural weight around it, and for one you get flight pay and you can receive combat medals, and for the other you can't. And again, and this is sort of, again, extrapolating from the undersea world, but there are many, many other examples of it, is that what we think of as autonomy really needs to be rethought of, as opposed to this is an autonomous vehicle, it's a robot in the kind of science fiction sense, and it's going to go out there and do its own stuff. It's really, autonomy is something that's bounded, and it lives in the time domain as a function of bandwidth and human context and the nature of the task at any given point. That echoes a report, for example, from the Defense Science Board in 2013. All autonomous systems are joint human-machine cognitive systems. There are no fully autonomous systems, just as there are no fully autonomous soldiers, sailors, airmen, or Marines. And then you could add to that engineers, undersea explorers, astronauts, automobile drivers, doctors, surgeons. Everybody's operating within a network, and the key is to understand what is that network and how does it work. So I'll give you a little excerpt from my previous book, Digital Apollo, that Owen mentioned, which illustrates some of this. And one of the real observations from that system, although it's from many, many others as well, is that when we think we have a system that's autonomous, they tend to work well kind of notionally in a laboratory environment. R&D loves autonomy. But as you get closer to real environments where there are real lives at stake and resources at risk, human interventions tend to be added at critical points. And so this is one of the reasons I think that you look at autonomy, and people used to say this about AI, sort of like, 5 years into the future, always has been, always ever will. Because it's much easier to imagine it in a demonstration kind of setting. And this is not an ontological argument. This is an empirical argument from tens and tens of studies that I've done of different autonomous systems over many decades, which is that as lives are at stake, as the stakes get raised, people naturally put in different kinds of human approvals. Again, what that means is the autonomy that we find in systems tends to be bounded in the time domain. Not to say that things aren't acting in certain ways automatically, but they tend to be bounded in the time domain. Classic example is the Lunar Landing. This is the last 200 pages of my book are all about the design of the last 10 minutes and the execution of the last 10 minutes of the landing, starting from 50,000 feet. You may well know that the computers and the software for this system were designed within a mile of this spot at what is now the Draper Lab, so it was then the MIT Instrumentation Lab. And when MIT first got the contract, they said, no problem, we can build a computer to land on the moon. And NASA said, what's the interface? And they said, well, the interface, all it needs is 2 buttons, right? One button is take me to moon, and one button is take me home. Okay? There again, that's the original notion from the kind of laboratory view out of what the autonomy of the lunar landing could be. It turned out that that was unacceptable for systems that had people on board. And in the end, there was a very, very rich set of interactions between the human and the machine. Now, interestingly, another one of the lessons which I'll come to appears here, which is that it was actually technologically much easier to make a fully autonomous landing on the moon than to make one that carried a person in it. In fact, Apollo 12 landed within 100 yards of Surveyor 3, which was an unmanned spacecraft, a robot, that had landed before Neil Armstrong landed on the moon. It was also sort of remotely controlled, but it was perfectly easy to do not perfectly easy, but it was you're perfectly capable to do a unmanned landing on the moon, and much simpler in many ways than a manned landing on the moon. Again, because of all the sort of baggage that comes along, but also just the natural safety and ethical considerations of what are you going to do with a system that could potentially kill people. This image is actually replayed on the cover of the book, although not as clearly. And this is what the lunar module cockpit looked like from Neil Armstrong's point of view at the moment that he reached up to turn off the automatic targeting system that he had been given and land the spacecraft in a kind of semi-automatic mode. This is the scene that opens the book, and sort of the whole book kind of orients around why did this happen. This image is actually a computer graphic image made for me by a guy named John Knoll, who is the chief animator at Industrial Light and Magic. Also, you may know him as one of the two founders with his brother or creators of what became Adobe Photoshop. And it's a historical document in that every switch and every light and every piece of data represented there is as accurate as we could make it. And you can see the crater outside the moon. Armstrong said, I turned off the automatic targeting because the computer was taking us into a rocky area, and I needed to tell it to go to a smooth spot that I could see. And that explanation, which is echoed almost exactly verbatim on all of the following 5 Apollo landings, where they all turned off the same targeting system at right about the same spot, really is an inadequate explanation for that, because the automatic targeting system, I don't have an image of it, was designed to allow them to interact with the computer and sort of set a landing set point based on looking out the window. You can see these little gradations just barely there. It was a kind of passive heads-up display, and he could actually jog the intended landing spot around with his joystick as many times as he wanted. And every time he did, the computer would recalculate a parabolic trajectory and bring him to that spot. And that system was designed so that it would converge on a nice smooth area. That's the system he turned off. He ended up landing in attitude hold mode, which had an automatic rate of descent, so it was by no means manual. But the New York Times the next day said, all praise the human intervention in the system. You know, people still have a role to play in the grand flow of history. It's a wonderful extrapolation of the biggest thing from the smallest moment. And so here again, you come to this lesson that greater autonomy is often an easier problem than autonomy with rich human involvement with the system, which requires more sophisticated technology. And a good example of this from the 60s is, you know, the Soviet spacecraft of the time all had analog electronic control loops, and therefore they were very highly automated. It was not easy to make those control loops places where the human could really intervene. It was a radical, very forward-looking step in the Apollo computer to put integrated circuits and make it a general-purpose digital computer and have it software programmable and all that. But one of the things that enabled was a lot richer interaction between the crews. And so I'll show you just a little bit of one way I'm trying to learn how to depict this graphically. And my postdoc, and Yanni Loukisis and I put together this app, which is basically we got the raw downlink from the LEM from one of the Draper engineers who had it on microfilm in his basement, something that NASA didn't have. We scanned it and OCR'd it and then reprocessed all the data, including the audio, into this sort of richer view of how this system actually worked. And what you're seeing here is time goes from left to right, as does the distance across the surface of the moon. And then the y-axis is a log scale of altitude from the surface of the moon. So the orange dots represent the lunar module, about 10 to the 4.5 from the moon at that 50,000-foot parking orbit. The slightly less orange dots are the Columbia, the service module, at about 10 to the 5.5, and then 10 to the 9th feet above the moon is Houston. And each of these dots represents an utterance by the crew in one of those spots. And then the lines are links when they have a kind of call and response relationship. And then up here, you see the utterances from all the entire ground control team, starting with the flight director here. And so what this little viewer allows you to do is sort of play through and scan through. And down at the bottom here, I should add, in fact, it's rare. I have not yet given a talk on this where the projector could actually display this part of the screen, but yours happily does, is the raw data from the computer. In this case, it's pitch, and these are various of the computer modes being indicated in the software. And then there's a little interaction where you can kind of turn off or turn on any of these pieces at any given point. And you can kind of play through. Of course, there's this famous 1202 program alarm, and I won't go through it all here. But you can play through the interactions between the crew and the ground, and you can see, among other things, the vehicle becomes a lot more autonomous in the last few moments before the landing as the ground kind of shuts up. But Aldrin and Armstrong are still very much talking to each other, and the data is all still being downloaded to the ground. And these are all their various interpretations of the data. I'll just let this play for a second.
Down 2.5, picking up some dust. Finish keep 2.5 down. Take shadow. 4 forward. 4 forward. Drift into the right a little. 6, 2.5. 30 seconds forward. Contact light. Okay, engine stop. ACA at a descent. Control both auto, descent engine command override off. Engine arm off. 413 is in. We copy you down, Eagle. Houston, Tranquility Base here. The Eagle has landed. Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again.
So that's the part that everybody's most familiar with, but you can also see here, if this is the pitch values here actually, this is where Armstrong turns off the automatic targeting and then goes through some pretty wild pitch gyrations. He himself called them spastic, as he tried to kind of get control of the thing and get over this crater. And I had never had, actually produced this visualization after I wrote the book, so I didn't have it when I did the book, but there was never really a way before to kind of understand this data all coordinated with the audio data and the trajectory data. And so it's just a kind of early attempt to say, how do we represent visually this rich sense of autonomy and how control is traded in real time back and forth through these systems? And then I'm also interested in how does that help you think about designing systems in the future? Also did a similar study of heads-up displays in commercial airline cockpits, which there's a lot of debate about. There's actually a lot of debate about whether airlines want to spend money on automatic landing, which has been around since the 60s and is a pretty robust system but quite expensive and keeps them rather far out of the loop. These heads-up displays, they're also not new as an invention, but they've come a long way in the last 10 years and they're becoming very practical. And they give the pilots a much better sense of being involved with the energy state of the aircraft at critical moments. And you can go back and look at even the Air France crash, but certainly the Asiana crash that happened in San Francisco last summer. There's a crash outside of Amsterdam in 2009. Any number of these crashes, there's a good argument that they would have been avoided if the pilots had been looking through the heads-up display. And the key thing there is the head-up display is not simply a representation of the data that's down below, but actually imposes a flight path vector on the scene the pilot's looking at, which is a kind of aggregate. Actually, one of the engineers who created the code for it calls it a manufactured product, which I love, because it's an aggregate of a lot of flight data that's filtered and smoothed in such a way that a human can follow it. And if the pilot looks at that flight path vector and puts it on the end of the runway, that's where the airplane's going to go, full stop. I mean, it's just as simple as that. And amongst the pilots, we did a whole project interviewing pilots from European Airline and American Cargo Airlines. There's a lot of debate about whether that represents a different way to fly or not, and whether it changes the nature of their task in what ways and what the advantages and disadvantages are. So I'll come back now to this Navy drones with a mind of their own. And this is really interesting to me because I was heavily involved in this project. It is a project done by Aurora Flight Sciences, who's just over here in the next building. And it was an Office of Naval Research project. And the goal was to build a full-size autonomous cargo helicopter. The Chief of Naval Research said, Amazon will give you a 2-pound book. I'll give you 1,200 pounds of supplies. And that was the goal. And originally, the sort of assignment from ONR was, make this thing fully autonomous with absolutely minimal dependence on a pilot or a human operator. And even just to get it to the point of a demo, piece by piece, that autonomy, again, got punctuated with human approval. So I'll give you an explanation of what this slide is. The vehicle's intended to come in. It has a super duper amazing LiDAR on it that was built for us by Sanjeev Singh and his group at Carnegie Mellon. and basically can scan the area, combine it with optical data, identify flat spots that have certain characteristics conducive to the aircraft landing, and then come in and land. And here's, you know, a for low resolution image of the map that it might make, some depictions of that LiDAR. Here again, to do this fully autonomously is relatively straightforward. In fact, Sanjeev's group at Carnegie Mellon had already done that fully autonomously. But remember what you're looking at in a real application. Here you've got a whole group of people standing around, plus a whole, you know, maybe their little compound and their equipment. And then you've got this, you know, 3,500, 4,500, 5,500 pound helicopter under autonomous control, screaming at them at full speed. And one of the assignments, one of the specs was you couldn't come up and sort of hover around and scan the thing. You had to come in at what they call a tactical landing, which is basically 90 knots and a very, very steep descent angle and very fast. Terrifying to the people on the ground. They don't know what the autonomy is going to do. These are all people who have worked in Afghanistan. We've did a lot of interviewing with them in Iraq, and they've seen autonomous vehicles flying around where they have no idea what they're going to do. You had to give them both a set of approvals and rejections, and also give the basic vehicle a kind of autonomy that the people could relate to so that they would understand what it was going to do. Down here on the left side, you see a little iPad mini interface that gives this radically simplified sense of what the vehicle's states are. In fact, I think there's only 3 of them. And as the vehicle comes in, it has to accomplish what we call a negotiation between the person on the ground and the vehicle itself. I want to land, you asked me to land there. That site isn't okay for one reason or another. The trees are too close. I want to land there. That looks good. Is that acceptable to you? Yes or no? And originally we had very complex ideas for how that negotiation might go. In the midst of the tactical landing, given all the speeds and physics and sensors, you had less than 30 seconds to accomplish that whole conversation. So that put real limits on how rich that interaction was going to be. But even for the Navy test range where we did this, we've never demonstrated this. It was just demonstrated in February. You had to have all kinds of safety considerations just to do it in a test setting, much less with real people standing underneath it. Here's an image of the helicopter. It's a Boeing Little Bird that's been modified to be fully fly-by-wire with the LiDAR on the front. And then instead of carrying people, it carries this enormous computer rack in the back. And here's the Marine on the ground who's supposed to be able to conduct that conversation with 15 minutes of training. And what you ended up having to do was create a basic, this is really not all that clear and the details don't matter, but the basic mission manager model, which was modeled in MATLAB Stateflow, is the state machine of I'm coming in, I'm either going to land or I'm not going to land. If I don't land, I may come around for one more pass, or I may go off and hold and give you this option. And that state machine had to be something that the human could understand easily, intuitively, and quickly. Couldn't be this rich, multi-layered thing. And we ended up creating that state machine and then auto-coding it into the autonomy, and also then as a crude working model in MATLAB of the GUI before operating the state machine directly and then porting that into the kind of iPad interface. So this was a bit of an experiment, although it worked very well, in saying, let's make sure that the issues on the human autonomy interaction are not interface issues per se. They're issues about how the core autonomy behaves at its most fundamental level. And you need to be thinking about all that and all that interaction in this very early sort of pre-coding phase in a way. And I'll just encapsulate that saying, if you want the human to trust the system, they have to have a mental model that's simple enough that they can relate to it, and that actually puts limits on the complexity of the internal state. You can't have the thing doing too much that people aren't going to predict. The Marines we talked to, and it was a pretty detailed kind of ethnographic study of maybe 60 or 70 people who had operated these systems. They said, the last thing I wanted to do was something I don't understand. Same thing, you ask airline pilots, you say, have you ever asked of your flight deck automation, what's it doing now? And every one of them will say, yes, I've had that experience. And then they'll say, you know, that's only what the beginners ask. The advanced users say, oh, it does that sometimes. But what then they said is, What we really want to know is, why did they do it that way? I don't care even if I don't like it or I disagree with it. If I understand something about the reasoning behind the states of the autonomy, it's much easier for me to relate to. And we've done some work on actually trying to communicate that from an engineering team to pilots. Then that gets you into one more observation, which is, if you really want the thing to do things that are what some people would define as autonomy, that is non-deterministic decision-making that's not predictable from a set of conditions that the designers may specify, there's all these things that you have to rethink. And I'll give you just one, which is sort of related: safety and verification and validation. Obviously, we fly in jetliners and airliners all the time that are heavily run by software. They're fly-by-wire, so software runs the basic control systems. Those things are certified. They're triply, quadruply redundant in some cases. How does that happen? Well, that software is incredibly highly deterministic and run through, in a very formalized set of processes, all the different possible ramifications, or as many as people can approach. You have to prove that every line of code has been executed, and the software has to be, the way you make certified software in the avionics business is to run through these very formalized procedures. There's not even a model for how to do that when you have systems where the decision-making may be non-deterministic and you really don't know what's going to happen. The DoD is very putting a lot of effort into trying to think through that problem, but it's going to be a huge issue for moving forward with higher levels of autonomy in a traditional sense. And the similar issues come around liability and testing and certification. And even, who are the users and what are they doing? Another interesting example with that autonomous helicopter is, so we've got this fancy LiDAR on there. It'll find you a landing spot and survey all the approaches and make sure you can get out of there cleanly and land you automatically. Well, if I was a helicopter pilot, my response would be, hey, I want one of those on my helicopter. It changes what you think of as a manned helicopter, and it changes what you think of as what you're doing there as an operator. Now that the pilot maybe doesn't have to worry about that. There's a supervisory control system that can give them input into those things, but many helicopter pilots have as their central sense of identity this sort of 2 hands on the stick, 2 feet on the pedals, come in and do the kind of detailed landing. So that's where kind of my final observation, the big advances I think that are required coming up are advances in these human relationships with systems. What do we think of as a pilot? What do we think of as an explorer? What do we think of as a scientist? What do we think of as a warrior? These are not things that are going to be cracked by kind of clearer interfaces or better designs of interfaces, nor solely by algorithms, but this whole kind of system progressing together, and new kinds of operators, new kinds of vehicles, new kinds of systems, and sort of rethinking the whole system. A good example of this is a current debate, which is, there's not a day that it's not in the paper, which is unmanned vehicles in the National Airspace System. And I think it's perfectly possible to imagine a regulatory framework that will allow that to happen, but it will have to change what human pilots are doing in manned cockpits as well. That's already changing in a lot of different ways, but you'll have to think about differently about what it means to operate a manned aircraft, which is, again, already happening for the last 50 years. So I'll leave it at that and leave some time for questions. Thanks for your attention.
I was wondering if you could say something about the relationship between humans and automation when the automation fails.
Okay.
For example, I was flying an approach on the autopilot a few weeks ago, and all of a sudden I looked down, the autopilot was not at all doing what it was supposed to be doing. I had to shut it off and land myself. So that was fine, but in a situation like an auto landing system where the response time is much shorter, some of those ramifications.
Yeah, that's a really good question, and that's actually a good example. And the most extreme case of that is the Air France 447 crash, where the pitot tube's iced up, the automation doesn't have the data it needs. Ironically, it actually did, and there was no reason that the system, given that data, couldn't basically, just using GPS guidance, kind of keep the airplane straight and level and bring it down to a safe altitude where it was easier to fly. But that's not how it was programmed. Again, autonomy is the assumptions of the designer being pushed forward in time. It was programmed to say, oh, air data's iced up, I'm out. See you guys, I'm out of here. Turns over the entire system to the crew, who are a little fatigued, a little distracted, in bad weather at night at very high altitude, where the angle of attack that's survivable in a big airplane like that is very, very narrow. And they actually had control of it for a minute or two, and then they lost control of it. And that highlights this case, and actually many of these other recent crashes do, where, you know, automation is always going to fail. Stuff just fails. We know that. And so you cannot design a system that keeps people so distanced from it all the time that they don't have that ability to intervene. And I've really, in the last 7 or 8 years, I've changed my opinion on this a great deal, because I was a much greater believer in kind of full autonomy. And when I started the Apollo project, I really believed it was the kind of full just macho-ness of the pilots that made them want that ability to intervene and get hands on the stick. But over time, and having talked to them about it and looking at other systems like the shuttle, I'm a lot more nuanced about it now. And so any system you have, again, think about an automobile or general aviation aircraft, very similar. You know, actually automobiles, I think, is a harder case, because things in aircraft actually happen relatively slowly compared to things in cars, because the distances to collision are greater. Even though the speeds are high, you've got a lot more space around you. The time constants are just slower. So any automated system in a car is going to have to be designed such that if and when it checks out, the person is going to be able to intervene in a way that they will find it at least safeable, if not continued drivable. And that's a hard problem that, A, we don't even understand very well. Again, Air France, we lost 250 people because of that problem. Clearly, there's a great interest and a lot of financial backing to understanding that problem. And B, we're just beginning to think about how to do that in a technical way. And again, you know, the Asiana crashes seems to be very much about pilots losing manual skills, and then for various reasons, there was a crash in Buffalo in 2009, similar story. When they're called on to execute those manual skills for a variety of reasons, they atrophy and they can't control manually. So again, it's an easier problem to design a system that's fully autonomous that never has people in it. But you won't stake human lives on that generally. And you know, my friends just lost their AUV deep off of New Zealand last week. Big deal. It imploded. Somebody's got to write an insurance check, but everybody's a little sad, but not all that sad. That's a whole different story than actually than scientists originally wanted to go to those trenches in manned vehicles. And you know, that would have been a whole different thing. Or what you end up doing is just certifying them so far that they become more expensive and whatnot. So I don't know if that answers your question, but very much an issue for a general aviation pilot too. And that happens all the time. And there are concerns in GA aircraft also. In fact, after doing this study with heads-up displays, I went and put a synthetic vision system in my aircraft, because I don't fly a lot of approaches at night in the mountains, which is traditionally what I had thought it was for, but it gives you a flight path vector. It's not a heads-up flight path vector, but if you have this 3D display displayed, then you have a flight path vector, and then you're always seeing where you're going, and it's that sort of aggregate that helps you just intuitively appreciate the energy state in different ways.
So the programming tools that you are using or that you're allowed to use, is that still in a state where dynamic memory allocation is not allowed and very primitive languages, or do you have more flexibility as long as no people are on board?
So that's an interesting question, because that was a vicious battle in the Apollo system. Was, do you have a preemptive multitasker or do you have a fully deterministic scheduler? And they ended up going with a preemptive multitasker, although there were bodies on the floor when they made that decision. And it's part of the book is a story about how the people who programmed that feel it saved the day in the end. Interestingly, like the 787, which is a fully digital airplane, it has a fully deterministic scheduler. The networks are all fully deterministic. There's no preemptive communications on the networks at all. And so at some level, the current state of certified avionics is behind where the Apollo system was in the 60s, although the last part of your question is a very good one, which is one of the real benefits of unmanned systems, and we saw this, again, way back in the 80s and the 90s, was, gee, you know, we would continue, you know, Jason would take 2.5 hours to go down into the seafloor just because it's very deep. So would Alvin. And with Jason, you could continue working on the code that whole time. That was valuable time. And then before you hit the bottom, you'd do another download of the code. And then the code actually on the vehicle doesn't do all that much in a vehicle like that. Most of it's topside, but same thing. Whereas, you know, in a certified manned system, all that code has to be done, you know, months or years ahead of time. Alvin to this day has no software in its critical loops. It's totally hardware operated vehicle in its native mode. So there's no software certification at all. That means that the unmanned systems tend to develop more quickly, and it's a lot easier to experiment with them. And you know, the barriers to changing and doing weird stuff is a lot lower. And that's, again, one of the things we did not expect when we started building remote systems in the ocean, and turned out to be one of the great advantages.
Would you say that you are forced to use tools that are maybe not as flexible as you wish, software-wise?
I'm sure
like
that's
advanced
true, yeah.
programming languages are not allowed.
Yep.
Isn't that a problem that if you use a more primitive language than you would like to, that there might be a higher chance of high-level bugs as opposed to?
Well, I'm sure that's true. That was certainly true with the Apollo system. Most of it was written in assembly code, and or in a very primitive kind of algebraic compiler, and you can imagine what it was like to debug that. That was a long time ago, but.
Just wondering, you touched a little bit on cars a moment ago in the failure case. If you could comment on autonomous cars or somewhat autonomous cars as all these principles apply to them.
Sure. I was sort of dancing around that topic because it's, and it sort of lurks behind the whole book in a certain sense. Again, I think, and I actually, all I know about the Google car is what I follow in the press, basically. But to begin with, and many people have said this, cars already have a lot of these little autonomy things built into them, from anti-lock brakes to cruise control to automatic transmission. I mean, you know, what is that if not a shifting of the operator's usage? Okay. And even there, even with your automatic transition, you still have a low 1 and a low 2 and some more these days. So even that system, which is from the 50s, has an ability for the human to kind of intervene and push that loop out. I think where it gets challenging is all the social dimensions of driving and all of the ways that people are making eye contact with each other and you know, perceiving, and you see this in the warfare context, actually. You know, it's for a machine, or even for a human looking through a soda straw video, to discern the difference between a wedding and a nefarious meeting with people carrying guns is not all that easy. And why? Because that's a social judgment that maybe some people can make, but the people who are doing the work are not trained to make those kind of judgments. And as you drive a car, you make those kind of judgments all the time. So on the one hand, you do basic collision avoidance, and that's easier these days to understand how you would automate that. And on the other hand, you're constantly saying, that car looks a little ratty and a lot of dents on it. I think I'll stay away from it. That person clearly is not paying attention when they're, you know, standing at the stop sign and whatnot. And you know, how am I going to interact with other people on the highway and whatnot? And again, I think automated cars are imaginable, but I think the whole system is going to change, and it's going to change what it means to drive. and even there, you know, people have a lot. It varies a lot. Okay, that's why it's hard to understand. When people have a lot of cultural connection to their identities as drivers, you know, and some people don't. Maybe some people don't care and they just want to go from A to B. That's certainly the case. Other people love their cars. They find an extension of their identity. They like the feeling of being in control and whatnot. And that varies as much as individual people vary. And so how do you kind of negotiate what people want at what level they want to be involved? But, you know, a good example of this sort of came up is automatic landing in airliners, okay, where automatic landing requires a tremendously high amount of vigilance on the part of the pilots. In fact, the stress levels, there's been studies that show that the stress levels on average are higher than they are in manual landing, because it's a little bit all or nothing. Either I have nothing to do and it's just going to land me, or I have to intervene at the last possible minute and bounce off the runway and go do a go-around. And, you know, I talk to pilots and they all say, you know, we like auto land. If we're tired at the end of the day, we sort of flick it on and it lands for us. It's not supposed to be for that, right? It's supposed to be, you know, legally they're supposed to have the very same level of vigilance. But over time, it gets used in a more, what's the word, complacent kind of way, and that's dangerous. And so when you know, and airline pilots or any pilots are highly trained, sort of technically astute, you know, they've had a medical exam in the last 6 months, you know, all these things. And you extend those kind of complex automation interactions issues to the world of millions of drivers. And to me, that's a very scary thing, actually. And you look at that Air France crash where, you know, airline flying is incredibly, incredibly safe, much safer already than driving is. And yet there are these corners of the state space where the people on the machine get into these wacky loops and everything just falls apart and goes to hell. And how are we going to learn about those corners of the state space in the human automated driving system? That's the question that really interests me these days.
Do you know of anybody who is sort of doing fault injection and testing on the way, sort of for humans? That is, if I know an airline flight is going to be boring, I can sort of check out if I'm the pilot. But if there's a chance that the thing's going to drill me, or it's gonna, you know, to keep me interested, and I can see that being extremely, I can see as a pilot being extremely feeling untrusted if I'm put in that situation. But I could also see it keeping me on my toes. Is there anybody who's doing anything in that direction?
Actually, there are some airliners that have like a very crude form of that, where like a little warning light goes on if nothing has been changed in the last 20 minutes or so. And that's a very simple form. I actually think that one of the frontiers for the work is to have the systems that run the aircraft kind of actively manage the cognition of the pilot a little more. Because we know that people get fatigued. And we know that people get less fatigued when they're engaged. And so there's no reason the system can't begin to engage the people. And, you know, frankly, it might be better for your pilot to be watching a movie than dozing off. And maybe their favorite movie is a better way of keeping them alert than pretending against all scientific evidence that they can spend 8 hours in front of a bunch of dials and remain their level of alertness. Same thing with napping, by the way. Like, we know it's better for people to nap for brief periods and they're more alert. Yet that's illegal currently in an airline cockpit, even though 85% of pilots will tell you that they do that. And so, and just those two issues begin to get around some of the cultural baggage around what do you expect your pilot to be. You expect them to be this kind of heroic, you know, active flyer, and if they're napping, they're clearly checked out, even though you have a set of research data that says people on the average over 12 hours are much stronger if they've napped for 10 minutes here or 20 minutes there. And so there's a whole set of things that you can begin to imagine. We're beginning to work on some of these things of actively engaging the cognitive state of the operator, but that requires changing what you think the operator is to be a little bit more mechanistic, right? and say, look, you know, and this is one of the things about learning to fly an airplane anyway, you just learn all these things about yourself where you really are a machine when it comes to fatigue, right? Your performance just degrades when you're fatigued, period, right? Your visual acuity just degrades when you have lower oxygen levels, period. You can't sit there and go, I'm smart, I can see better, right? And so there's a kind of cognitive extension of that, that the regulatory system and what we expect out of our pilots is not remotely caught up with. And so there's a lot of things you can imagine like that, and that may be the case in cars too, right? Where, in fact, I think, you know, even some of the kind of lane departure warning sort of things, they only work if your hands are on the wheel. So you can't fall asleep and let your Mercedes S-Class drive you. You have to stay like this, and that's one way of sort of keeping people vigilant. Does that answer your question? Yeah.
All right, well,
Okay.
thank you very much.
Great. Thanks for your attention. Good question.